All right. So instead of streaming directly to YouTube, I'm now recording onto the hard drive, and then I'll upload everything at the end of the class. Just because the Wi-Fi here does not seem to be very stable for me, and it just interrupts the stream, and then I have to end up using a lot of extra time to restart the stream and so on. So I'm just going to record the entire thing, and that also gives me a chance to do some editing in case I said anything that is inappropriate in class. So I can just kind of beep that out. But I promise I won't be speaking like what's his name? He played the guy with an eye patch in MCU in the Avengers.
Oh, Samuel Jackson.
Samuel L. Jackson. Yes. Yep.
That
And
would be
he.
hilarious to watch on YouTube, though.
Yes. Yes. Beep 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 beep. You fuck beep. But that's well, he did that to every single character that he played. So so that's kind of the fun thing about him. All right, so we are now done with two's complement, which is a way for us to represent negative values, but only using zeros and ones. So I'm hoping that particular module is okay with you guys, because what we are talking about today is the comparison of values. So looking at a bunch of zeros and ones, how do we know whether one is representing a value that is less than the value of another bit pattern? So it depends on whether it is signed versus unsigned. So that's where we are going today, which is binary comparison. And today's lab is subtraction and compare. So I will release that in just a little bit. All right, so we're going to go into the module first. And we'll start with only less than is needed. So the first section here basically says you don't need anything else. All you need is to know whether a value is less than another value or not. Because from that and also logical operators, we can get back to, well, by changing the position of the operands, we can get greater than, but then we can also get to less than or equal to by using a negation. We can also get to greater than or equal to using a negation. We can get to equal to. Well, okay, let's get to not equal to first. Because A does not equal to B, mean A is less than B or B is less than A. So once again, we use an or and then we flip the order. So we can re-express equality using less than. Once we can express not equal to, then we can also express equal to, because equal to is just the negation of not equal to. So the bottom line is we only really need to know whether a particular value is less than another value or not. Section 2 is long, and well, I take it back. Section 2 is not long. It's just introducing how we interpret a bit pattern. So I'm just going to skip all the way to the notation itself. One is VU, which stands for the value interpreted unsigned. That's what a U is. And one is VS, and you can probably guess what this S is representing, signed. So this is the value interpreted signed. X is a bit pattern, and the bit pattern needs to have at least m bits, but it can have more. So we are basically saying x is a bit pattern, and m is telling us how many bits are we interpreting out of the bits available in x. Are we doing okay so far? I can give you an example later on. Okay. So with VU, it's rather simple, because I think this particular summation, we have seen this many times. The first time we saw this was when we talked about base conversion. In other words, when you look at the least significant m bits of x, what we are doing is we are setting up a loop where the index variable I is starting from 0. It goes to and include m minus 1. And then for each iteration, we produce a value which is based on xi, which is a single bit, a binary digit. It can either be a 0 or 1, times 2 to the power of I. In other words, I is corresponding to the bit position that we are examining. And once we have all of those terms, we add them together. That becomes the unsigned value of a particular bit pattern. Are we okay so far? Okay. Well, let's go check out Zerno because I want to give you guys an example just to be sure that we understand what that is all about. This is from my other class, but I think we can safely reuse the same instructions. So what we have here is, let's take a look at 1111, okay? So when you look at 1111, VU Y4 is 15. This is not X, this is Y. It has exactly 4 bits, so we are looking at the unsigned interpretation of the value of the bit pattern of Y using the least significant 4 bits, which in this case, basically they are all the bits. So why is it 15? Because it is 1 times 1 plus 1 times 2 plus 1 times 4 plus 1 times 8. 1 plus 2 plus 4 plus 8 is 15. Are we doing okay so far with this particular example? We can look at another example, like, let me see if I can scroll down. Okay, so that is not the right window. Let me go find the right window to scroll. There we go. So we can also look at 0, 1, 1, 1. So when we look at the pattern of 0, 1, 1, 1, which in this case is X, so the unsigned value of X as a bit pattern, which is 0, 1, 1, 1 in this case, using only the least significant 4 bits, but that turns out to be all the bits that X has, would be 1 times 1 plus 1 times 2 plus 1 times 4, but 0 times 8, because the bit position corresponding to 2 to the power of 3 is a 0. And that's why the sum is just 7. So are we good? Are we okay with the signed interpretation of a particular bit pattern up to m bits? Which is essentially exactly the same thing that we talked about when we talked about base conversion. Except in that case, I said, okay, let's imagine that we have an infinite number of digits, both to the right-hand side of the decimal point and also to the left-hand side, we just have a lot of zeros, padding. But in this case, it's very specific. We only want to look at bit 0 up to bit m minus 1. All right, so if that part is okay, then we move on to VS. Okay, this is the signed interpretation. So this is another way to look at a bit pattern where it can potentially be representing a negative value. So let's take a closer look at this and compare between this particular definition and this definition over here. The first part of the signed interpretation looks almost exactly the same as the signed interpretation, only with one minor difference. And what is that minor difference?
It doesn't go to n minus 2. It doesn't go to n minus 1. It
It
goes to n minus 2.
Exactly. So the bit for position m minus 1 is not included in the sigma notation. Instead, it is pulled out of the sigma notation and becomes its own little term. So you look at that term and go like, well, we are still multiplying x subscript m minus 1 to 2 to the power of m minus 1. So what is the big deal? We are not adding, we are subtracting. That is the big deal. That is why a signed interpretation can go to negative values. Are we good so far with this? Okay, so now let's take a look at the signed interpretation of a value and see how it can represent negative values. So I'm switching back, again to Zerno. Oh, nope, nope. This is the one that you can see, and this is where I can scroll. So we're going to go back to the 1111, which in your case is over here. So we're looking at Y, which has a bit pattern of 1111. So when you look at a signed interpretation of Y using only the least significant 4 bits, it is representing negative 1. Why is that? It is because we have 1 plus 2 plus 4 minus 8. So 1 plus 2 plus 4 is 7. 7 minus 8, because of this particular bit here, is negative 1. So this is yet another way to find out what value is being represented by a binary bit pattern But this time I did not need to rely on 2's complement. So this is a slightly more straightforward way to figure out what value is being represented if we choose to look at the bit pattern as a signed integer. Are we good so far? Are we okay with the VU versus the VS definitions? And those definitions are right here. So this is the unsigned interpretation, this is the signed interpretation. Are we okay? Are there any questions? Because if there are questions, now would be a good time to ask.
Could you flip it back to the other page?
To Zernal?
Yeah.
Oh, sure. Let me switch to. There we go.
So that same 4-bit pattern
Mm-hmm.
that we saw in, okay.
Yeah, so you can see how the same bit pattern, which is Y in this case, which is 1111.
Okay.
In the unsigned interpretation, it is 15 because we are adding the 8 to the 7.
Mm-hmm.
But in the signed interpretation, the interpretation is -1 because we are subtracting the 8 from the 7.
Okay, so the front bit in this situation determines whether or not it's negative, right? So if it's 1,
That
it's
is
positive.
correct. Okay. Because no matter how much you can add up, using the least significant bit other than the most significant bit, you can add up the powers of 2 corresponding to all the other bit position.
Right.
But the most significant bit is representing a value that is guaranteed to be greater than the sum of all of the other bit positions added together.
Correct.
So that's why when the most significant bit or the signed bit is a 1, it guarantees the signed interpretation is going to be negative.
If the leading bit, specifically that 4-bit slot, or are we talking
the most significant bit? So if you're dealing with 8-bit numbers,
yeah,
then it's going to be bit 7 because
right,
it's going to be more to the left hand side.
And in our case, because there's 4 bits, the most significant is going to be number 3, right?
Yep, bit 3. That is
and
correct.
If that one's a 1, then it's automatically negative.
Yes. The only question is how much, how far to the negative side.
Okay.
Yep, that is correct. And you can also see, you can also see in this case, this is x. So x turns out to be 1, 0, 0, 0 in this case. So when we look at the sign interpretation of x using only the least significant 4 bits, it would be 0 of 1 plus 0 of 2 plus 0 of 4, which all adds up to, guess what? A big fat 0 minus 8. And that's why it is representing -8 when you look at x from a signed perspective or signed interpretation. Is that okay? Is everybody with me at this point? You're good? All right. So now what we're going to do is to take a look at something else because the whole thing, what section 2 is trying to set up is to give us the vocabulary to understand section 3 and section 4. In other words, these definitions here are just helping us to understand the proof of why we can use one particular bit to see if the minuend is less than the subtrahend when both are interpreted unsigned, and how we can also figure out which one is less, or whether the minuend is less than the subtrahend when we are dealing with signed interpretation. So this is really just adding to our vocabulary so we can have a discussion. Okay, all right. I think this is a unique, well, I wouldn't say unique, but this is an opportunity to kind of demonstrate what math is really about. Math, is many things, but being a language is one of those. It is a way for us to express certain things. Because without these notations, then it becomes much harder for me to express what it means when we look at the unsigned interpretation versus the signed interpretation of a bit pattern up to only m bits, using the least significant m bits. All right, so let's move on to section number 3. So when you glance through section number 3, which I hope most people have done over the weekend, because that's how you can succeed in the class, okay, is to spend some time to kind of preview what you're going to be dealing with, on the following week, because your mind at least you'll get an idea of what we are going to talk about. So with this stuff here, only two sentences are really important. The first one, which is in a binary subtraction of two m-bit patterns, x minus y, tm equals to 1, t subscript m equals to 1 if and only if vuxm is less than vuym, assuming t0 is a 0. That is the summary of this entire section. Well, let's go ahead and try to interpret that statement first and find out exactly what it means. Okay? What this means, okay, the first sentence here is if you choose to look at the bit pattern x and the bit pattern y as unsigned values, okay, if you choose to say, okay, both of these two bit patterns are representing unsigned integers, then T of m, which is the carry bit that is hanging all the way to your left-hand side, that thing is a 1 if and only if the minuend, which is x, is less than the subtrahend, which is y. Now, what does that mean? That means after a subtraction, you can tell whether x is less than y by only looking at the borrow, not yeah, by looking at the borrowed bit that is belonging to position m. All right? Is that okay? Okay. May not be okay. So let's go ahead and do some exercise. Okay. Uh, I can see my journal on this side, but I don't want to just kind of give you, um, what I already had. So I'm going to write something on the whiteboard. There's no need to write it down because the actual thing. Well, okay. Let me think about this. I probably want to just do it in journal so you can see it. Okay, give me a second here to set it up because I need to set up a new page. And then I can write on. Because I was thinking right before the class that I can be a little bit lazy today by reusing the handwritten stuff from the Thursday class, but then I decided against it because that will not be it's not going to give you guys the extra time to kind of think about it, look at the puzzle and then go, okay, what are we going to do here? All right. So what I'll do is I'm going to give you a live example of 0, 0, 0, 0 minus 0, 0, 0, 1. And this is also a good exercise to remind us how to perform binary subtraction by hand. So we have x, we have y, we have q, we have t, and then we have d. So if anyone is still wondering what those letters are representing, I'm going to have to say, like a broken record, need time to review past material, like seriously review the past material, because we have been using these symbols for some time already. And if you remember from the statement, we are also saying, well, it kind of depends on the assumption that T0 is a 0, so we put a 0 over there first. So now we can go ahead and perform the actual subtraction. Q in this case is R of xy, and R in this case, because it's in binary, can be done using exclusive OR. So that means we're just looking at the exclusive OR between x and y. So this is a 1. Those are all zeros in this case. So the Q row is easy to figure out because it's just the exclusive OR between the x and the y. The T row, on the other hand, is a little bit harder because T of I plus 1 is what? B of xi yi or B of qi ti. I really hope that is familiar at this point. Let me write it down here just so that you guys can see it. Okay, your T of I plus 1 is B of xi yi or B of qi ti. And what is B of something? B of ij is not I and j. I'm using the shorthand here. What looks like multiplication is conjunction. Exclamation points is still representing a logical negation. So this should be very familiar at this point. If it is not, I would definitely try to study really hard before the first exam on next Wednesday. All right? And there's no guarantee that even with a lot of studying it's going to help. But without a lot of studying, not being familiar at this point with this stuff here, is almost a certainty of not going to be doing well in exam one. I'm not sure how many of you want your professor to be brutally honest, but I feel it is my obligation to be such, with such honesty. Is that okay? You still got a week and a half, or more than a week, so there's still time to make up for this. Okay, so now we look at the 0 minus 1. Okay, so we have b of 0, 1, which is a 1 already, which means we're going to have a 1 over here right away. And then we look at, oops, we look at 0 minus 0. B of 0, 0 is going to be a 0, so no problem there. But the b of 0, 1 is going to be a 1 because we have these two being ORed, so that means we end up with a 1 over here. And it's going to be the same argument of why we have a 1 over here, and it's going to be the same argument why we have a 1 over here. So that means we do end up with b of 4 is a 1. From the statement that I said earlier, what is this going to imply? If I just know that b of 4, or b of m, in this t of m, sorry, not b, I used the wrong letter in this case. Let me change that. So t of 4 in this case is a 1. What is that telling us? Based on the statement that we just saw earlier, let me go back to that slide so you know which statement we are referring to. So based on this statement, oops, okay. That happens because, there we go. So based on this statement here, in a binary subtraction of two m-bit patterns x minus y, tm is 1 if and only if vu xm is less than vu ym, assuming t0 is a 0. So based on this statement, and based on what we are seeing here, t4 is a 1, what can we conclude? Not negative. There's nothing about negative here because these are all unsigned representations.
Representation is negative. Does that work?
No, it has nothing to do with negative. But I think you have the right idea. It's just when you verbalize it, you're referring to something that should not happen in this case because it's an unsigned comparison. So there's nothing negative here. So instead of saying negative, what do we say?
Greater than 0.
It has to do with greater than, except it's the other way around. I only want to hear less than in this class.
That means it's less than 0.
What is less than what?
Oh.
Let me switch back to that slide so you can see what is less than what. Okay, so in this particular statement, you only see less than in one place. What is that? VUXM is less than VUYM. What exactly is VUXM? It's the unsigned integer represented by the bit pattern of X, right? And that is less than the unsigned integer that is represented by Y. The M is not really useful here because we're using the entire bit pattern, so M is not exactly doing anything useful here. So if we switch back to the example here, it is basically saying, the bit pattern of 0, 0, 0, 0, if we interpret it as an unsigned integer, that value is going to be the unsigned value of 0, 0, 0, 1. So this is a conclusion that VU of 0, 0, 0, 0, which turns out to be actually 0, is less than VU of 0, 0, 0, 1, which turns out to be 1. is true. Is that right? Does anyone want to challenge that 0 is less than 1? Okay, very good. You look at this and go like, wow, that is a lot of trouble just to know that 0 is less than 1. Indeed it is. All right, so we're going to look at the second example. And to look at the second example, I'm going to scroll down a little bit here. And this time we have 0, 0, 0, 0, minus 1, 1, 1, 1. And once again, this is a great opportunity to practice binary subtraction. So 0 minus 1 is a 1 with a borrow already. 0 minus 1 is a 1 with a borrow already. 0 minus 1 is a 1 with a borrow already. 0 minus 1 is a 1 with a borrow already. And then 1 minus 1 is a 1. 1 minus 0 is a 1. Minus 1, 1 minus 1 is 0. 1 minus 1 is a 0. 1 minus 1 is a 0. All right. So what is relevant in this case to what we just talked about? None of the other bits matter. All we want is to know what is T4. T4 is once again a 1, which means what?
Less than 0.
What is, no, nothing is less than 0 in this case. Nothing can be less than 0 if you're looking at the unsigned interpretation. Why? Say that again? Yes, that is correct. So you address the original question. The VUXF is less than VUYM. So let's address that first, and then I'll go back to the earlier question of why there's nothing can be less than 0 when you're dealing with unsigned interpretation. So let's go ahead and just write this out. VU of 0, 0, 0, 0, which really literally is 0 of 1 plus 0 of 2 plus 0 of 4 plus 0 of 8 is 0. And that turns out to be is less. This is a question. Is it less than VU of 1111? VU of 11114. Okay, I'm forgetting the 4 for M here because we're using all the bits, so I'm just abbreviating and not include the 4. So when you look at 1111, it is 1 of 1 plus 1 of 2 plus 1 of 4 plus 1 of 8, which turns out to be 15. So does anyone want to argue, that 0 is not less than 15? Okay, 0 is less than 15. It's pretty clear. Okay, this is true. But we also have T of 4 being a 1 in this case because this is T of 4. Right?
Right, because M says
M is 4. Yep, M is 4 in this case. So let me get back to the earlier question of why can't we have anything being less than 0 when you have the unsigned type?
Is it because unsigned it goes from 0 to 2W minus 1?
Exactly. The smallest value of any unsigned interpretation is 0 itself. You cannot have anything less than 0 if you're dealing with unsigned interpretation. So in the C++ program, okay, if you're looking for a condition of something being less than 0 and that something turns out to be an unsigned type, you have an infinite loop. If that condition is in a loop, it's going to be an infinite loop because that condition will never be, well, actually, I take it back. It's not going to go through one iteration because the condition is always false. There's no way anything can be less than 0. Are we doing okay so far? So we're going to take a look at 2 more examples, and I ran out of space here, so I'm going to have to use a new page again. And this time we are going to look at, okay, we can look at this, 1, 0, 0, 0 minus 0, 0, 1, 0. Okay, there we go. All right, so we have to assume T0 here because the statement says that we have to assume T0 is a 0 to begin with. So now we say 0 minus, okay, the first row, this is the Q row, is the exclusive or between the first two. So we got 0, 1, 0, 1 over here. And then we have no borrow to digit 1, so that's going to be a 0. But we do have 1 borrow of over here, and then we have one borrow over here, and then we have no borrow over here. And then when we do the exclusive OR of the Q and the T to get the D, then we have 0, 1, 1, and then another 0 over here. So if this process is looking a little foreign to you, you probably need some more practice with how to perform binary subtraction by hand, using the definitions that we have talked about in this class. All right, so, but the bottom line here is we are looking at T4. T4 in this case is a 0. So what is the conclusion? So because T4 is a 0, the conclusion is VU of x, which is 1, 0, 0, 0, is 0 plus 0 plus 0 plus 8. So that is an 8 being less than VU of y, which is 0, 0, 1, 0, which is a 2. That is false. Okay, very good. Because what we see here is, hey, T4 is reflecting whether the less than is true or false, right? Because in this case, the less than is false, and T4 turns out to be 0. So it's very consistent. Every single time T4 is a 0, x is not less than y. Every single time that T4 is a 1, um, x is, yet x indeed is less than y. Does that make sense so far? Okay. So we're going to I'll give you another test case here. Okay, I'm going to cheat a little bit and go back to the notes on the other day. Okay, so we got 0, 1, 1, 1 minus 1, 1, 1, 0. So once again, we have 1, 0, 0, 1 over here. This has to be a 0. That's a 0 because we don't have any borrow. This is a 0 because we don't have any borrow. This is a 0, we don't have any borrow. This is a 1 because we have a 0 minus 1. And then we do the exclusive OR down here. And this is the result. So in this case, T4 is indeed a 1. VU of 0, 1, 1, 1 is 7 in this case, is less than VU of y, which is 1, 1, 1, 0. And that turns out to be 14, is true. Cool. Okay, so once again, it is consistent. The less than is true, and T4 turns out to be a 1. So it seems to us that we can rely on T4 to reflect whether the unsigned integer represented by x is less than the unsigned integer that is represented by y. This is just a demonstration. So just because I can show you a few examples of how this works, is that conclusive that this is a reliable method? We only have to look at T4 to see whether x is less than y.
How does that one get there? The last one?
Which one?
In the T row? Yeah.
This one here?
Yeah.
Because remember, one part of T of I plus 1 is B of xi yi. This is xi, this is yi. But B of xi yi is the same thing as not xi and yi.
Mm-hmm.
So not xi is not 0, not 0 is a 1,
Mm-hmm.
1 and 1 is a 1.
Okay.
Yep. All right. Any questions about this? So I know I'm going to sound like a broken record because I am. You probably want to have all the definitions, at one place. Collect all the definitions of all the symbols and all the operators and stuff like that, and put it in one place, just so that it's easy for you to look up and reference the definitions, because you will probably need to look up those definitions. By now, in order to succeed in the exam, you not only want to be able to put all the definitions together, you really should have those somewhat memorized in your head. Now, for some of the really odd things, maybe you just go like, okay, I kind of need to look it up. So you have you have it in your notes. But the in truth, okay, you really should have used it in when you work out these exercises, to kind of have to Okay, I know how to use it now. So how do you give yourself exercises? Because that's going to be the next question. It's like, but Tack, you never gave us a lot of exercises. Use a random number generator. Okay, you just use a random number generator to generate a number between 0 and 15. In fact, generate two numbers between 0 and 15. Your first exercise is to convert those things into binary representation. Okay, so now you have two 4-bit patterns. And then you say, okay, what do I do when I add those things up? Okay, that's one exercise. What do I do when I subtract those things? That's your second exercise. So you need to be confident that you can do all of that stuff in binary by hand. Because once you understand the process of how to do it by hand, then you have a improved chance of succeeding in exam one. Okay, so that's kind of one of the exercises that you can do. All right, so getting back to what we are talking about here. Remember the question that I asked earlier was, so from these examples, it seems like T4 being a 1 is a reliable way to tell whether the last than is true or not. But do we have an official proof of that? We have some observations, but do we have a formal proof? Nope, we do not. Okay. So that is why you see a lot of stuff, under the statement, under the only statement that really matters is a proof. Because everything else in section 3 is this can be proven as follows using proof by induction. Now, do you have to know proof by induction in this class? The answer is no. Okay? The question then is why do you put the proof into this module if it is not needed for this class? Because some of you might have taken CISP 440 already. And if you have taken CISP 440, proof by induction is one of the concepts introduced in that class. So you should be able to somewhat follow through this proof here using what you have learned in CISP 440. Someone may be saying, but I took CISP 440 last semester. I really don't think I need it. I don't think I need that knowledge ever again. So why do I want to be reminded of all the pain and suffering in CISP 440? Well, then my question is, are you planning to transfer? If you do plan to transfer, what can you expect at a 4-year university? And that's a question that I'm not going to answer because you can go to the the university that you plan to transfer to, look up their program, look up their degree program, and see if you can find, classes that rely on proofs. Okay, and I guarantee you there is at least one, possibly two, classes that would still rely on the concepts that you learn in CISP 440. Because all we teach here at a community college can only be equivalent to lower division classes at a 4-year university, which basically means every single class that you take here is, is, is instrumental to be successful in one of the classes, the upper division classes at a 4-year university. So you really cannot afford to say, okay, the semester is over. I don't need to know this stuff anymore. You still kind of need to retain all that stuff. And this is one opportunity for people to practice what they have learned in a different class. So if you're thinking, that's fine. I have not taken CISP 440. I can safely ignore this entire proof. Well, I wouldn't say you're wrong, but I would say when you do take CISP 440, if you remember that you saw a proof by induction earlier in this class in CISP 310, you might want to kind of come back here onto this slide and go like, okay, now I should have the right tools and understanding to figure out what is going on with this proof. Do you have to do it? No, you don't have to do it. But this is one way you can get extra practice when you are crossing content from different classes. All right, so there is that. So section 4 talks about signed interpretation, and it has one single statement that is really important, and this time it is at the end of the entire section, which is this little section over here. I know most of you cannot see it in the back, so let me change the screen size and kind of change the position a little bit. so you can see it. Unfortunately, when I resize it, it put it into a different screen. So I just need to put it back here and resize it like that so people in the back can see the bottom, the last sentence. Okay, so the last sentence says if we define L to be S, what is this symbol again? Exclusive OR, very good. Okay, good job. So if L is defined to be S exclusive OR with O, this is uppercase O, then L equals to 1 if and only if VSXM is less than VSYM. Got like, okay, so let's pick up the stuff that we should know already by this time, okay? I think we should understand what is VSXM versus what is VSYM, right? The signed value, the signed integer represented by X versus the signed integer represented by Y. Okay, we got that. We know what is exclusive OR, and L is being defined here. So what is left is, okay, but what is S and what is O? So we go backward a little bit. This is how my son read novels. He starts with the end, and he goes back up. Sometimes he opens the book in the middle, and he do the binary search thing. He would go like, okay, from the beginning, I can kind of guess what is the premise, and in the middle of the story, this is what happened. Let me guess what is happening in between. So he would read the book in a random order. He does that all the time. All right, so the first thing we notice is, oh, okay, so O is defined here. This is why the overflow flag is defined as blah, 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 okay? So the most important keyword here is it is defined. Overflow or big O is defined to be blah, 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 gibberish, okay? But what does that gibberish mean, okay? You can probably say out loud x subscript m minus 1 and not y subscript m minus 1, m minus 1, and not d subscript m minus 1 plus or not x subscript m minus 1 and y subscript m minus 1 and d subscript m minus 1 is the big O or the uppercase O of overflow flag. That doesn't tell you much, okay? What is significant about m minus 1? You have an m bit integer, so that bit is not just any bit. Go ahead. It's the most significant bit, okay? Remember what we talked about earlier? If that bit turns out to be a 1, then the value being represented is guaranteed to be negative. I don't need to care about what the other bits are. I just know that it is negative. The value is negative, right? So, okay, so that means the most significant bit of x and the negation of the most significant bit of y and the negation of the most significant bit of d or blah, 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 that is of significance somehow. Okay. So now what is not clear is the sign bit or the S bit. So let's try to figure out where S is defined. Oh, right here. S is defined to be D subscript of M minus 1 as a shorthand. So in other words, what we just call as the S flag is simply the sign of the most of the difference, which is the last row. Are we good so far? So now we know what is O, we know what is S, we also know how L is defined. Yep.
I'm sorry, this is probably an obvious question, but what is D again?
D is the difference. It is the last row of a subtraction. So let me go back to Zernal. So now we can go back and look at the things that we have done so far. This row here is D. It is the difference. It's the actual result of the subtraction. Okay? So we'll figure out what this D is supposed to be. We have a 1 here, 1 here, 1 here, and a 1 here. All right, so with this done, we want to apply what we have just learned, okay? So I'm going to use a different color. Let's try blue here. What is the sign flag? What is the S flag in this case? Remember, the S flag is D of M minus 1. M is 4 in this case, so we are looking at D3. So where is D3? Where can I find D3? Yep, exactly. So this is D3. which is otherwise known as the sign flag of the subtraction. Okay, it is a 1. Okay, very good. All right, it's time to take roll. So we'll take a short break from this discussion. And I'm going to take roll. All right. I'm just going to borrow this one, or maybe this one. There we go. So I'll let you know when you can refresh Canvas and answer the question. So first thing is to change this to 0919 because today is September 19th. And then in terms of the question, the answer is overflow. Very appropriate. So overflow is the word. And I'll give you guys some time to answer this. So I'll give you until 11:30 to answer this question. Save and publish. So if you refresh your browser, you should be able to see the row taking activity being below binary comparison. Let me show you where you're supposed to be able to find it. Right here. So this is, from your perspective, it is right below binary comparison because you cannot see the lab just yet. And the word is overflow, all lowercase. So when you guys are all done with this, I will continue with how to figure out whether the first number is less than the second number from a signed integers perspective. All right. Does anyone need more time for row taking? Nope. Okay. Then we shall continue. All right. So when we continue, we look at this, and now we want to figure out what is overflow. So overflow in this case. So okay, do you guys remember the equation? Let me just kind of slap the equation here so it's easier for you guys to see how to figure out the actual value. So let me give me a second here and just copy and paste this into the other onto the other side. This is really a nice little tool because I can just copy and paste. And let me show you this part here, and then I will find a place to put it. There we go. That's a good place to put it. Okay. So now that we can see, what how O is defined, what is x subscript m minus 1, which is the most significant bit of x?
0.
0. Okay, very good. So we have a 0, and what about y subscript m minus 1? It's also a 0, which is here. Yep. All right, so we put another 0 into here. And the negation of the most significant bit of D, what is that? Oh, that's a 1, okay? Or the negation of the most significant bit of X, and the most significant bit of Y, and the most significant bit of D, okay? All right, so what are we looking at here? This is 0 and not 0 and not 1. Well, I think the left-hand side is going to be a 0, right? Because in the conjunction, we need just one of them to be a 0 for the whole thing to be a 0. On the right-hand side, we have not 0, which is a 1, but then we have a 0 again. So both sides are zeros, so the OR between the two sides is going to be a 0 as well. So now your overflow is known to be false. We do not have what we call an overflow. What about the L flag? Oops. I have to make sure we're still recording, which is good. I think my palm just touched something. So what about the L flag here? The L flag is the S flag exclusive OR with the overflow flag. What is the sign flag again?
1.
Sign flag is a 1, and the overflow flag is a 0. So we have 1 exclusive OR with 0, which is 1. Very good. All right. So what about that? Do you guys remember what the L flag is representing? Let me go back to the slide again so that you can take a quick look at what the L flag is trying to say. Okay, and that we have to scroll down a little bit. Where's my mouse cursor? There we go. All right, so the last portion here, okay, where my mouse cursor is running over, that is how we utilize the L flag to try to come up with a conclusion. So this time we do have the L flag being a 1, and according to this statement, L equals to 1 if and only if the signed integer represented by x is less than the signed integer represented by y. Okay, so we need to check whether that is the case or not, right? So now we switch back to Zernal, because now we need to figure out, okay, let me go back to the black pen, the signed value of 0, 0, 0, 0. In this case, okay, I just have to say once, it is none of 1 plus none of 2 plus none of 4 minus none of 8. What would that be?
Nothing.
Big old 0, right? Okay, so that's not surprising. And what about 1? Vs of 0, 0, 0, 1. That is still just 1, because in this case we have 1 of 1 plus none of 2 plus none of 4 minus none of 8. Okay, that's still just 1. So in this case, we now say, well, that is true too. So as it turns out, the L flag 1 does seem to match the result of the comparison that x is indeed less than y. Are we good so far? Does anyone want to argue that 0 is not less than 1? No one. Okay, very good. So this one seems to be easy. I mean, all that extra work to come to the same conclusion, I mean, that seems kind of silly. We'll now take a look at the second one, the second case. So we'll see whether it is just going to be as trivial in this case. All right, so first of all, we need to find out what is the sign flag. Where's the sign flag?
In row D.
In row D,
The third one, so the fourth one across D3.
Yep, exactly. So it is a
0.
0 in this case. Okay, so I'm going to circle it just so that we know which one is the sign flag, and it is a 0 in this case. But in order to know the L flag, we also need to know the O flag, right? So what is the O flag? Well, the O flag is, I'm just going to use a really quick, oh, this is the wrong place to do it because I need that space to do something else. So I'm going to put it down here. So O is, in this case, just want to use the same notation that we used earlier. So let me scroll up, find out how we use that. Well, I suppose we can just copy and paste it too. So let me see how to do that. Nope. And then we want to do a copy and paste. There we go. Nice. All right. So based on this, what is it going to be? The most significant bit of x is a 0. Oops, wrong tool. And the most significant bit of y is a 1. The most significant bit of d is a 0. Or the negation of the most significant bit of x and the most significant bit of y and the most significant bit of d. All right, so when we look at these two conjunctions, what is your conclusion?
0.
Yeah, exactly. Both of them are going to be 0 because I see a 0 over here. I see another 0 over here. So each conjunction has at least one 0. So each conjunction is going to be a 0. And then when we look at the disjunction of two zeros, it is also going to be a 0. Okay. Okay, let me just make it very clear which one is a 0 and which one is an uppercase O. So I put a stroke or put a strike across a 0. At least when O can be confused with 0. All right, so we know what is S, we know what is O. So now we can say what is L. L is S exclusive OR with O, and S in this case is a 0. O is also a 0. So that means the exclusive OR between those two is a 0. Okay. So now we want to look at the signed interpretation. Vs of 0, 0, 0, 0 is 0. Vs of 1, 1, 1, 1 is what? How do we look at Vs? How do we look at the signed integer represented by 1, 1, 1, 1?
So you know it's gonna be negative.
Yep. Okay, yep, go ahead.
It's the first three digits minus the last digit, so.
Exactly. So we got 1, 1 plus 1, 2 plus 1, 4 minus
8.
8. So we got negative 1, right? Okay. So we put a negative 1 here. And this is a question whether it is less than or not. This is false. Okay. And then we look at the false here. We look at the L flag. They seem to be consistent. Very nice. Let's do 2 more examples unless you guys say, no, we are good. We don't need more examples. Should we do more examples? Yeah, I think so too. I think so. More examples is always good. All right, so we got these. Okay, we got one more here. And that's good. I will give you guys one more example later on. All right, so let's take a look at this one. We have the sign S flag being a 1, and then the overflow flag, in this case, oops, wrong place to put that. The overflow flag in this case, because we can still refer to the equation, which is right here. So we can just go ahead and figure out what is overflow. So in this case, overflow is going to be 0 and not 1 and not 1, or not 0 and 1 and 1. Is that making any sense? This 0 comes from here. This 1 comes from here. This 1 comes from here. Remember, we're only looking at the most significant bits of x, y, and d. Or if you want to use mathematician terms, we are only looking at the most significant bits of the minuend, the subtrahend, and the difference.
So we don't care about Q.
Hmm?
We don't care about Q.
Sorry?
We don't care about Q.
Q? Yeah, Q and T are not used,
Okay.
to, in the calculation of overflow. So what is that going to be? Well, let's see. This time we have 0, not 1 is a 0, not 1 is a 0. We have all zeros on one side. Okay, that's going to be 0. But on the other side, we have not 0, which is a 1. So we have 1 and 1 and 1. We do have a 1 this time. And this is an OR, which means if at least one side is a 1, the whole thing has to be a 1. So this time we have overflow being a 1. So now we can look at the L flag, which is the exclusive OR between the sign and the overflow. The sign is a 1. The overflow is also a 1. So the exclusive OR between those two is a 0. Okay. So from the statement that we saw from the notes, you probably would be guessing, so that means the signed integer represented by x is not less than the signed integer represented by y. So we'll go ahead and figure that out. Okay, we'll actually check it out. So Vs of 0, 1, 1, 1 in this case is still 7 because we have 1 plus 2 plus 4 minus 0 of 8, which means it's still just 7. Vs of 1, 1, 1, 0, on the other hand, is 2 plus 4 minus 8, right? Because we have 2 plus 4 but we have to remember that we are subtracting the 8 represented by bit 3. So what would that be? 2 plus 4 is a 6. 6 minus 8 is negative 2. Very good. And we are asking, is the minuend, which is 7, less than the subtrahend, which is negative 2? I don't think so. Okay, we say this is false. So once again, the L flag reflects the correct result of the comparison because we only care about whether the minuend is less than the subtrahend. The answer is no, it is not in this case. Are we good so far? Do you see how the L flag is kind of magical? Okay, we have one more example, which is the other way around. Oh, okay, I think I know what. Oh, right here. Actually, it's right here. Okay, I did have the last example. I just forgot to scroll all the way down. All right, so we're gonna work on this one. This is our S flag, which is the sign of the difference. It is a 0. So once we know that, we want to figure out what is O, the overflow. In this case, the overflow is 1 and not 0 and not 0. Does everybody can you guys all see where the 1 is coming from, where the second 0 is coming from, and where the third 0 is coming from? This is the 1, this is the middle 0, and this is the last 0. Okay? And then we have an OR, not 1 and 0 and 0 in this case. So what have we got here? Not 0 is a 1, not 0 is a 1, so we end up with 1 and 1 and 1 in this case. Well, we don't need to look any further, right? Because this is an OR, so that means if at least one side is a 1, the whole thing has to be a 1. So now we say, okay, we do have an overflow of 1 in this case. Now we can try to figure out what is L. L is the sign flag over exclusive OR with the overflow flag. The sign flag is a 0 this time. The overflow flag is a 1 this time, so we do have a 1 for the L flag. So what that is telling you, if what I stated earlier is true, that means the signed integer represented by 1000 is less than the signed integer represented by 0010, right? If everything works out. So we want to double check. So now we look at VS of 1000, which is what? Nope.
Oh, yeah.
Negative 8. Negative 8, because remember, whatever the most significant bit is representing, whatever power of 2 it is representing, we are subtracting that from the sum of powers of 2 of all of the other bits. So in this case, the other bits are all contributing nothing. So we have 0 minus 8, which is negative 8 in this case. So this turns out to be negative 8, and we are now asking, is it less than the signed integer represented by 0010? Well, 0010 is still just representing 2. So the answer is, yeah, I think so. I mean, negative 8 is less than 2. Sounds good to me. So true seems to be consistent with what the L flag is indicating. So magically, okay, so magically the way we define the L flag is the correct indicator of whether the minuend is less than the subtrahend if we choose to look at both bit patterns as signed integers. Are we okay so far? Yep.
And if they're both false, it's just equal, right?
Hmm?
If they're both false, it'll be equal.
No.
They'll be equal to each other.
No.
If the top one is less than is false and the bottom one is less than is false.
Okay.
If they're both false.
If T4 is false and L is false, that then XY has to be the same. We saw one case like that, I think, and that was not the case. So I think we got a case. Oh, I guess we don't have a. Okay, so let me construct a case like that, both being false. Okay, so the question that was asked is if T4 is a 0 and L is a 0, does that mean the two values are the same? The answer is no. So the question is, how do we construct a case like that? So we want the signed and the unsigned interpretation to be both false or not less than. Oh, that's an easy one. 0, 0, 0, 1 minus 0, 0, 0, 0. That will illustrate this particular example. So I'm going to use the same procedure as before, even though it's not really needed in this case. This is an easy one. So exclusive ORs, okay? These are all exclusive ORs of x and y. And then 1 minus 0 and 1 minus 0 do not have a borrow of 1. So that's a 0 over here. 0 minus 0 does not have a borrow. 0 minus 0 does not have a borrow. So we end up with a 0 here. Same argument, same argument. And then we have 1 minus 0. Well, these are all exclusive ORs. Okay? So that's the result. So now we want to say, okay, what about the other bits? What do we know about this? So T4 in this case is a 0 because that is T4 right here. And so we look at VU of 0, 0, 0, 1, which is really just 1, being less than VU of 0, 0, 0, 0, which is really just 0, is false. Because 1 is less than 0 is false. Now we look at the other one, okay? And this time I'm going to have to use a different color. This is our sign flag. So sign is a 0. What about overflow? Overflow is 0 and not 0 and not 0. Or, let's see, not 0 and 0 and 0. Does everybody know which 0 came from where? Because they're all zeros, so it can sound very confusing, right? The first 0 comes from the most significant bit of x. The second 0 comes from the most significant bit of y. The last 0 comes from the most significant bit of d, okay? But doesn't matter which way you look at it, this whole thing has got to be a 0. So let me erase this extra stuff that's here. Okay. Now that we know the sign flag and the overflow flag, we can compute the L flag. So the L flag is the sign over exclusive OR with the overflow, which is 0, exclusive OR with 0 in this case, which is a 0. So let's check out the VS. Okay, that really is a 1. Oh, I'll take it back. We are looking at signed interpretation. So this VS of 0, 0, 0, 0 is still a 0, and that is false. So this time we have false, false for both T4 and the L flag, and yet 1 and 0 are different. The reason why we cannot say, okay, if they're both false, it has to be the same, is because they're both looking in the same direction. They're both trying to tell us whether x is less than y, except one is looking at the signed interpretation, that's the L flag. The other one is looking at the unsigned interpretation, that would be the T4. Are we okay so far with this? So once again, the question is, well, according to our observation, the way we define the L flag should work. But is that conclusive that this is how it will work with all possible cases? Once again, the answer is no. Okay, and that's why there's a lot of stuff in the module that basically shows how we can prove that or how we derive the sign flag. That's what all of the other stuff is about. Okay. So one more thing that that might be on your mind is, why is the overflow the overflow? What does it mean when we look at the overflow? So the overflow basically means when you look at the D or the value represented by D, it makes no sense, or the sign of the D makes no sense. So I'll go ahead and try to explain that with all the examples that we have seen so far. Okay, so you guys can focus on this side, and I'm just going to scroll around on the other side, like right here. Okay, so I'm going to use a dark green color to look at Vs of D. So Vs of D in this case is 0, 0, 0, 1, which turns out to be 1. Okay, so now the question is, does that make sense? Does the sign of the difference make sense in this case? I don't even care about the value. I just want to look at the sign and see if it makes sense. If you subtract a negative value from a non-negative value and end up with a non-negative value, can that happen? You start with a non-negative value, like 0, 2, 4, and so on, and then you subtract a negative value from it, like -5, -1, -3, and the difference, the result, turns out to be non-negative. Can that happen?
I think it only happens. Right?
Well, no, not
Are we
only,
saying
but
we're saying the difference between a positive and a negative
you're
number?
correct. It only happens. It really cannot go negative, right? It can only be positive because you start with something that's non-negative and you subtract a negative quantity from it. So it can only end up with a non-negative quantity. So in this case, yeah, I think the sign of the difference makes sense, right? That's why overflow is a 0. The sign of the difference is okay. It makes sense. All right, if that one is okay, let's take a look at the second example. So from your perspective, we are looking at the second example here. So in this case, overflow is a 1. So that means that if we just focus on the difference, the sign of the difference should not make sense. So let's check it out. So Vs of the difference, which is 1, 0, 0, 1, is 1 minus 8, which is -7. Well, okay, does the sign make any sense? I don't even care that it is -7. I just want to look at the negative here and go like, does that make sense to you? We start with a non-negative quantity. We subtract its negative quantity from it, and somehow we end up with a negative quantity. Well, based on what we talked about earlier, this does not make sense. The sign itself does not make sense at all. That is why we have the overflow of 1, because you end up with a value that cannot be represented in 4 bits anymore. Because the actual result is what? The actual result is, this is 7 minus -2 should be a 9. But if you look up the table, if you remember from our last week's discussion, we talked about the range of a 4-bit number as a signed number. It can only represent values from -8 to +7. +9, which is what we really want to end up here, is not representable using the signed representation. So that is why we end up with an overflow. 2 more examples, okay? Yeah, because I just want to make sure that we understand what overflow is really trying to say. Okay, so now we actually have 3 more examples, but that's okay. Okay, let's look at this example over here. Overflow is a 1. But does that make sense? We have a negative quantity minus a non-negative quantity, ending up with a non-negative quantity. Does that make sense to you? So on the number line, I started off with something to the left of the number line, and we want to subtract a non-negative quantity, which means I want to keep going in that direction a little bit more. But I somehow ended up with a value that is on the right-hand side from your perspective of the number line. Doesn't make sense, right? But if you look at Vs, it will show you exactly why it doesn't make sense. Because Vs of the difference, which is 0, 1, 1, 0 in this case, is really just 6. So we're basically asking, we have -8 minus 2, but we end up with 6, like +6. That doesn't make sense. I don't even care about the quantity, just the sign itself does not make sense. So that's why the overflow is a 1 in this case. So the way overflow works is it really just look at the sign of the minuend, the subtrahend, and the difference. So anytime you subtract a non-negative quantity from a negative quantity and end up with a non-negative, it's a problem. That is taken care of using the first conjunction. The second conjunction handles the case where you start off with a non-negative quantity, you subtract a negative quantity from it, and then you somehow end up with a negative quantity. No, I take it back. You start off with a non-negative quantity, you subtract a negative quantity from it, and you end up with a negative quantity. That's handled by the second conjunction. Is that okay? More or less?
So what are we doing with the overflow now that we know whether or not it has overflow?
So
Are we
the
using it
overflow
to
by
see-
itself doesn't have a whole lot of use, okay? Particularly in C and C++, because in C and C++, if you have, let's say, an addition or subtraction,
Yeah.
where the result is out of the range of what a signed integer can represent, it will fail silently. In other words, it will just do the binary subtraction. Whatever the bit pattern is the result of the binary subtraction, it just puts it back into the expression, and that's it.
Right.
So it doesn't give you a warning or doesn't give you an exception of, hey, we have a problem here because the result of this subtraction or addition is outside of the range of what we can represent, which is what Visual Basic will give you. Visual Basic would actually give you it's not a segmentation fault, but the program will basically pause and it's going to complain with a window, saying line so and so has a problem because the result is out of the range of what can be represented. But C doesn't do that. So that means the overflow flag by itself is not utilized in a program written in C or C++. But what we use O for is to combine O with a sign flag. So normally, without overflowing, the sign flag by itself can tell us whether the minuend is less than the subtrahend, just because of the nature of subtraction. But in the case of having an overflow situation, the sign flag will indicate exactly the opposite of what it is supposed to be. So that's why, if you just look at the sign flag, you go like, okay, if we did not have overflow, this would be sufficient. This would be fine. But because we can have an overflow situation, and when we do have overflow, the sign flag indicates exactly the opposite. So that's why exclusive ORing, the sign flag with the overflow will give you the right answer. It's kind of like this. The sign flag is always going to give you an answer, but it can lie.
Gotcha.
And then the overflow is the lie detector.
It checks it.
It's the lie detector. So if the answer is yes, but the lie detector says also yes, that means the original answer should have been a no.
So L is the true sign, like it's the true, like representation of the number?
Yes. But if it is out of range, that would be wrong. It would not give you the correct conclusion of whether the minuend is less than the subtrahend.
If it's out of range.
If it is out of range. Because without out of range, the math is really simple. Because in algebra, if x is less than y, right, and you subtract both sides, if you subtract x from both sides, what do you get? You get 0 on one side, y minus, the other way around. So if you subtract y from both sides, what do you get? You get x minus y is less than 0, right? And guess what is d? Without overflow, d is exactly x minus y. So you end up with d being less than 0. But how do we know d is less than 0 in the sign as a signed number? We just have to look at the most significant bit, because if the most significant bit is a 1, then the quantity represented by d is negative. So that's why without overflow, the algebra says, hey, we just need to look at the S flag, because the most significant bit of the difference should tell us the right answer already. But with overflow, it is going to be opposite of what it's supposed to be. Is that okay?
That's kind of hard to wrap my head around. That last part.
The last part?
Yeah, that's kind of hard. That's just kind of hard to.
Because by definition, d is the difference of x minus y.
Right.
So that's why we can go from x minus y, go to d, and from here to here is just subtracting y from both sides of the inequality. So I'm just trying to explain why normally the sign flag alone will give us the right answer, but when you have an overflow, then it's not going to give you the right answer.
Okay, that's just what we're saying. We're just stating that.
Yep. So it's kind of like, the Joker will always give you an answer when Batman asks him a question, and then Harley Quinn is the lie detector. Harley Quinn can say whether Joker is lying or not. So if If Joker says no, and Harley Quinn also says no, so that means the real answer is really no, because Harley Quinn says, the Joker is not lying when he said the answer is no.
But in this case, you're saying that only if we have a Harley Quinn, because sometimes sign can tell you the right answer by itself.
Right. So Harley Quinn in our case is the overflow flag.
Yeah.
It's basically the lie detector of the sign flag.
Okay.
So when the overflow flag is a 1, then it's saying, oh, no, that sign flag is lying. But in this case, lying is easy to fix because the answer is either true or false, right? So if it is not true, it has to be false. If it's not false, it has to be true. Are we doing okay so far? I know we are running out of time in the lecture, but I do have one more thing to bring up, before I release the lab. It is something for you guys to do when you before Wednesday, because if you have time to do it, it'll be great. If not, it'll still be okay, but I would much prefer that you guys have some time to take a look. So if you go to the announcement of this class, I did release the policy, exam policy and the preparation guide. So if you have a chance to read, that would be great. Okay. I also gave you exam 1 from spring 2022. So you have all the tools, you have all the knowledge to approach exam 1 at this point. Because it is all about subtraction. It's all about multi-digit subtraction, sometimes in binary in base 2, and other times in base 3, I think, in this case. So you can remember, this is just a practice, okay? It's a dry run for you guys. So I would advise you guys to try to do this as much as you can before Wednesday, because I'm going to tell you about the answers on Wednesday. The other thing that I think is also important is are these two. Exam policy you have to read. Okay, I'm going to make the assumption that everybody would have read the exam policy before our exam. The other one, which is the preparation guide, is optional. Okay, if you say I know how to study for exams already, I know how to take an exam already, I don't need this, that's fine. Okay, you don't have to read it. On the other hand, if you say, well, I kind of want to know what TAC has to say about the exam preparation, then you can go ahead and click on it, and it gives you the my take on how to prepare for an exam. Particularly, I think one section is really particularly useful is I have had people asking me for a study guide. Until that person asked me, okay, until I became a professor, I was never familiar with the concept of a study guide. I never knew there is such a term called a study guide. And yes, I did graduate from college, just in case anyone is wondering. Um, so I looked it up, okay, and there are some links basically to suggest how you can come up with your own study guide. Because it is supposed to be an individual kind of journey. No, I'm not Buddhist, but I'm quoting certain things that might sound Buddhist. But it's supposed to be an individual journey. Everybody has his or her own path in this case, because we all learn material differently. Everything is represented in a different way. So some people like a graphical representation with tons of arrows flying everywhere. That's how they like to visualize the concepts. Other people like me like equations. I need to know the definitions. I need to know how the symbols relate to each other. So it is up to you, but I provide at least 2 links so that you guys can kind of follow those links. And then there's a little reverse timeline of what to do at what time, blah, blah, blah. It's only a suggestion, okay? And there's no guarantee that by following this, you're going to be very successful. It's just, what I can think of, as a recommendation. And that's all it is. All right? Okay, so the practice exam is also released in the announcements in case you did not catch that. I'm hoping everybody's getting email from the announcements, because if you're not getting email from the announcements, you can be potentially be missing a lot. So this is the exam 1, which is a link to a Google Doc. And what you can do, okay, this is the Google Doc. So what you can do is to go to File, and then you go to Make a Copy, so you can have your own copy. So then you have something to work on, just electronically, or if you choose to print it out, that's okay too. Okay, work on it on a piece of paper. It's up to you to decide how you want to approach the exam from last semester. All right. So on that note, I am going to release the lab for today. And it's not going to be a really hard lab. Some of the definitions that we talked about today is repeated in the lab. So you don't even have to kind of cross-reference to today's lecture too much. All right, so I just need to make sure. Okay, show the correct answer for this class, it's 1:30 p.m. There we go. Oh, I forgot to show you its flags. The access code of the lab is just flags all lowercase. All right, so there you go. You can take a short break if you want to. And I'll probably try to leave the classroom at exactly 1:30 today because there's a party downstairs and I want cake. All the unhealthy stuff, they're usually tasty. Frosting. Hmm? Sorry? Oh, it's just downstairs. It's the classroom right below this. Yep. One of our office personnel is promoted, but moving to a different campus, so we're just sending him off.
Congrats.
Yeah, yeah. I wish he would stay here. That we have a position for him here, but we don't.
Doesn't always work out that way.
Yeah, he's really good with the CIS. I mean the BCS division too. All right, I'm gonna turn off the screens just so that burn off the bolts. Oh, and I can upload today's lecture.